Hello, my name is Ralf Kruse from Mitutoyo Europe, and in this presentation I will explain about TAGLENS and a pulsed light source. So what is the content of the presentation? I will start explaining about the TAGLENS components. Then I will explain about the TAGLENS principle. And next, I will show what is a pulsed light source and how can it be used in combination with TAGLENS. At the end, I will show some typical features and applications for TAGLENS. So, what is TAGLENS? Where does the name TAG comes from? T stands for tunable, A acoustic, G gradient index. TAGLENS is an ultra-fast lens capable of varying the focal position. So let's start with the TAGLENS components. The basic components consists of a TAGLENS controller and the TAGLENS main unit. The TAGLENS controller is controlled via a software called KSC. This is a standard software that comes with the TAGLENS and is necessary to run the TAGLENS and all of its features. The KSC comes with an SDK, a software development kit. So it's easy to integrate all functions that are necessary to run TAGLENS in an own software. An additional software package called TAGPack-E is also available. This software has some features for image displays, like a viewer, and using some different filters like EDOF, the extended depth of focus, using multifocus, sharpening filters, and so on. Also, this software comes as an SDK, software development kit. Therefore, all the features are easy to integrate in an own software environment. Optional components are also available. A special designed pulsed light source for TAGLENS is available. I will explain the main features of this pulsed light source in another section. And also a video microscope unit, VMU, for TAGLENS is available. And this video microscope unit is easy to use, integrating the TAGLENS in an entire setup where you just have to combine an objective lens, an illumination, and a camera and get very easy ready to run video microscope unit with different magnifications with the features of TAGLENS. So now we have seen the different components, and in this section I will explain about the TAGLENS principle. So how does TAGLENS works? What is the principle? TAGLENS is a liquid lens. It has a fluid, a silicon oil that is surrounded by piezo elements. So it's a cylinder in a housing with piezo elements filled with a silicon oil liquid. On the top and bottom side of this cylinder is a window with an aperture of about 11 millimeters. Here you also can see the bottom side with the window. The piezo elements generates a radial standing acoustic wave in the liquid in the silicon oil due to interference. This acoustic wave due to the interference generates a density variation in the liquid. And with the density variation, you also get a variation of the refractive index. So density variation corresponds to refractive index variation. On the left part, you see the picture that illustrates a high refractive index, therefore a high density in the center, and a lower density, therefore refractive index in the outer part. In the middle image, we have a homogeneous situation of the density distribution and therefore an homogeneous refractive index. On the right part, we see a picture with a low density in the center and a high density at the outer part. Therefore, also low refractive index center, higher refractive index in the outer part. So we have different distributions of the refractive index. So we have situations where we have a high refractive index in the center and going to lower refractive indexes to the outer side. We have situations with a homogeneous refractive index. We have a situation with a low refractive index in the center of the TAG lens, homogeneous high refractive index again. This situation continues all the time. So here is again the illustration of the TAG lens. Parallel light goes through the TAG lens in the situation with a high refractive index in the center. This lens, TAG lens, works like focusing optics. So it focuses the light beam here, and in combination with an objective lens with an own focus position, a total focal point at this height will be generated. The situation with the homogeneous refractive index, light will go through without focusing, defocusing effect. So the focusing effect just comes from the combined objective lens and generates a focus position here at a little bit farther position. Defocusing effects with objective lens will generate a focus position here at the farthest position, and then it goes back to the homogeneous situation focus position like here, and then focusing effect here. So this cycle continues all the time during TAG lens operation. And the cycle time of this TAG lens cycle is 14 microseconds. That corresponds to a frequency of 70 kilohertz. So the TAG lens cycle frequency is 70 kilohertz, means one cycle from here to here is 14 microseconds, shifting the focus position from close to far, back to close distance within 14 microseconds. If the combined optics has a specific depth of focus, this depth of focus region will be shifted with TAG lens to a far and low position. Every objective also has a native depth of focus. Depending on the magnification, the depth of focus varies. Low magnifications means high depth of focus. High magnification means low depth of focus. Therefore, you see, if you have a magnification like 1020x, the depth of focus of the objective lens itself is in a range of a few micrometers, 3 micrometers, 50x, just 1.8 micrometers. Small magnifications, 1x, has a depth of focus of 880 micrometers. The TAG lens now shifts this region of depth of focus of the native optics back and forth in a high range. Therefore, we generate a depth of focus of the same optics in combination with TAGLENS to 16 millimeters, from 880 micrometers to 16 millimeters. This is a factor 18. So we increase the depth of focus of an optical setup with this objective lens by a factor of 18 if we combine this objective with a TAGLENS. Also, the other magnifications, we have a factor of 22, 23, and for the higher magnifications, it's lower but still significant. So in total, the depth of focus will be increased dramatically using the TAGLENS. So a general overview of the TAGLENS principle and cycle. So the piezo elements modulate acoustic wave in the fluid. Therefore, the gradient index changes with the same frequency as the piezo elements vibrate, making a focusing situation, a focus point at this position. Or if the gradient index is lower in the center, we will have a defocusing situation, and this changes frequently with 70 kilohertz. In combination with an objective lens, we generate a near focus position or a far focus position with a frequency of 70,000 times per second. Since a camera frame rate usually is much lower, we generate all in focus images on a camera frame. So here we see some typical examples. The red marked is standard optics without TAGLENS. The green marked is the standard optic combined with TAGLENS. Example is the cutting edge of a drill. We see just the tip in focus with the standard optics. All the other parts are out of focus. We only get some parts of the electronic boards of the components in focus, but the board itself is out of focus, or clock gears where we have just one gear in focus and other gears with different distances are out of focus. Images in combination with TAGLENS, same optics with TAGLENS using the extended depth of focus. We see here all in focus image, everything is in focus. Also on the electronic board, we see everything in focus, even for different distances, and also for the clock gears, all the gears are in focus. So to summarize, what are the benefits of TAGLENS using this a standard light source, a continuous light source? So the main advantage is the TAGLENS increases the depth of field or the depth of focus by a factor of up to 23, depending on the optics. So we get a much higher depth of focus. The scanning frequency is very fast, 70 kilohertz. Therefore, even for moving parts like an inline application, TAGLENS is capable for. The TAGLENS does not use any mechanical moving parts, and it generates all in focus images, even for 3D workpieces that can be used for inspection or defect detection. So even if different heights or 3D structures are on this workpiece, or the workpiece itself is curved, the TAGLENS enables an optical setup to get all in focus images. Therefore, a TAGLENS optics is very robust against position tolerances, even If we are not perfectly on the focus position, we get focused images. And this is not very usual for liquid lenses, but the tag lens can be mounted in arbitrary orientation, vertical or horizontal. So now we talked a lot about a tag lens and how it can be used using standard light sources, CW light sources. Now we switch to pulsed light source. What is a pulsed light source, PLS? So the pulsed light source, specially designed for tag lens, generates very short pulses. If we look here at the tag lens cycle up and down for the focal position, Y is the distance, X is the time. So this is a typical tag lens cycle, 14 microseconds from minimum to maximum again. 14 microseconds means 14,000 nanoseconds. And the pulses of this special designed pulse light source are very, very short in a range of 50 to 100 nanoseconds. So within this pulse time, the distance of the focal point varies only very, very little bit. So therefore, it's possible to pick a specific height in focus using the pulsed light source. By shifting the pulse to different positions, it's possible to pick different layers in focus. One example, how to use a pulsed light source that is synchronized with the tag lens face and the camera. We can pick only one layer in focus. If we have a structured sample with different heights, and we illuminate during our tag lens cycle at a very specific point in this tag lens phase where only this position is in focus, we can pick one layer in our camera image that is always in focus, layer A, because only at this point the focus is really illuminated. Please keep in mind the tag lens cycle is 70 kilohertz, 70,000 hertz. A typical camera frame rate is 70 hertz. Therefore, 1000 tag lens cycles are on one camera image. Another mode using the pulsed light source in combination with tag lens is multiple focused layers in one image. So in one camera image, it's possible to not just pick one layer in focus, but it's possible to use the pulsed light flashing different layers, different positions in the tag lens cycle, and therefore pick different layers in focus that are combined in one camera image. So in this case, A, B, and D layers are in focus because we tune the pulsed light to exactly these points in the tag lens cycle where these layers are in focus. Another mode using pulsed light source with tag lens is shifting the focus after each image. So we capture an camera image where we pulse at a specific layer where our position A is in focus. And for another camera image, we shift our pulse to a different point in the tag lens phase where we have a different layer in focus, in this case B. And then we can do this also with another camera frame to another position and continuously. Up to 20 is possible. Here 4 are shown. And then switch back to A and so on. So we see many different operation modes are possible with TAGLENS, and the possible modes are mainly distinguished of the different kind of illuminations. Using a standard light source, a CW continuous light, the main feature of TAGLENS is generating an extended depth of field, all in focus images. Even for different heights, we get every part in focus in a single camera image. Pulsed light um, is optional and allows different modes like a high speed focus. So generating different points in focus in one overview, generating different planes in focus that can be picked by the phase of the pulsed light. It's also possible to generate 3D images. So a composed 3D image is possible using focus stacking features and combining this to a 3D image. And by calibrating the phase of the pulsed light, we have height informations, and therefore it's possible to generate 3D height maps. So these are some features possible with TAGLENS using CW light or pulsed light. 3D presentations with pulsed light, it's possible to switch between different modes. It's possible to integrate the TAGLENS in robots or using it for defect detection software. It's possible to build an autofocus system without any moving parts or using focus stacking algorithms and so on and so on. So in the last section, I will summarize the main TAGLENS features and show some possible applications. So TAGLENS with CW light. So with the continuous light, the main goal is to extend the depth of focus. Depending on the objective lens that is combined with the TAGLENS, the extended depth of focus range will be extended by a factor of 22, 23 maximum. So this results in all in focus images, even for 3D structures and curved surfaces. Typical examples are optical inspection, defect detection, inline image capturing, and so on. TAGLENS with a pulsed light, we saw we have a lot of different additional features. It's possible to generate an autofocus system without moving parts with TAGLENS in combination with a pulsed light source. Feature of focus stacking is possible. It's possible to generate 3D presentations, point clouds, height maps, and so on. Examples where these features are useful is optical inspection with a high-speed autofocus system without moving parts, microscopic height measurements also with high speed, and fast autofocus for inspection. Even with lasers, TAGLENS can be used, but in this case, the TAGLENS only can handle low power lasers. Low power means maximum 500 milliwatt per square centimeter. The TAGLENS generates a laser line instead of a laser point, usually using a laser. With an optics, it generates a focus point with a high light or energy density. And with TAGLENS, it's possible to shift this point back and forth that it generates a laser line. So a typical example where this is useful is in the microscopy using fluorescence. Thank you for your attention. If you have further questions, please don't hesitate to contact us. Thank you.